What if every device you owned, from your smartphone to your smart fridge, suddenly lost its way in the digital world? Unable to find another, unable to connect. It sounds like a tech apocalypse, right? But without the unsung heroes of network addressing, that's exactly what our interconnected lives would look like.
It's true. From the cloud to your coffee maker, everything is connected, and it all starts with data communications.
Absolutely. And before we really dive into how all this digital magic happens, if you're looking to cut through the noise and get truly well-informed, or maybe you're just insanely curious about the digital highways that power our world, please take a moment right now.
Yeah, definitely do this.
Go ahead and like, subscribe, and share this deep dive. You really don't want to miss insider tips that could help position you for a bright future in your chosen careers. And for access to additional resources that will supercharge your learning, maybe give you that competitive edge, be sure to check the description for this deep dive.
It's all there for you.
Okay, so today we're embarking on a really crucial journey, a deep dive into the fundamental concepts of network addressing. I mean, this is the very backbone of how devices on any network, anywhere, find each other and communicate, well, seamlessly.
Exactly. And our mission, especially for you, our future business and IT leaders, is to, extract the most important nuggets of knowledge. We're drawing heavily from CompTIA's Network Plus Guide and other expert sources.
Right. We're aiming to transform these complex information systems concepts into clear, practical insights, giving you a firm grasp on the essential managerial and technical issues in data communications.
We'll journey from the basic structure of how data travels through the intricacies of IPv4 and its evolution
to the expansive future of IPv6.
Yeah. And along the way, we'll explore the critical services that manage these addresses, DHCP and DNS, for example.
And arm you with powerful troubleshooting techniques so you can become like a true network detective.
This deep dive is really designed to prepare you for those industry-standard network certification exams and help you excel in your careers.
Whether you're studying BCIS 1347 right here at Tarleton State University's Dr. Sampak College of Business, or honestly just passionate about mastering the digital landscape. Okay, let's unpack this with maybe a real-world scenario. Imagine you're sending a critical business report, not just across the office,
right,
but across the globe, maybe to a client in Singapore.
Yeah, a long way.
How does that digital parcel containing maybe highly sensitive data find its way through countless interconnected networks, bypassing congestion, navigating multiple digital borders? Well,
at its core, this intricate ballet, as you called it, is the job of what we call the network layer. Think of it as the internet's sophisticated postal service. Or maybe more accurately, its advanced GPS and logistics hub.
Okay.
This is layer 3 in the OSI model. That's a conceptual framework that helps us understand how different network functions operate. Its primary role: to ensure that your digital data, often bundled into what are called datagrams or packets, can travel reliably from its source all the way to its destination. Even if that destination is literally halfway around the world, crossing many, many different network segments along the way.
And the unsung heroes of this digital postal service must be the routers. These aren't just simple switches. They're like intelligent intermediate devices acting like the sorting offices and traffic controllers in our digital world.
That's a great way to put it.
They receive these datagrams, meticulously inspect their destination, and then make incredibly intelligent decisions about the best path to send them next, getting them closer to their final recipient.
Yeah, and it's a complex dance, but it's handled by two distinct operational planes within the network layer. Each one has its own crucial responsibilities.
Planes.
That's right. First, we have the data plane. You can imagine this as the actual delivery trucks and their skilled drivers. This plane is focused on the tangible tasks, moving data efficiently and
safely.
Just getting the stuff there. Exactly. Its functions include receiving the packets, carefully inspecting their destination information, and then forwarding them along the most appropriate physical or logical path. And crucially, if the network experiences congestion, like digital rush hour traffic, the data plane is also responsible for queuing these packets. This ensures they still get where they need to go, prevents loss, and ultimately guarantees their safe and reliable delivery.
Okay.
It leverages fundamental low-level protocols like Internet Protocol, IP, and Ethernet to actually physically move that data across cables and through the air. It operates at a lower abstraction level, concerned primarily with the direct movement of data based on the instructions it's given.
So if the data plane is the delivery truck, What's orchestrating all those routes, making sure the trucks take the most efficient path?
Ah, that's where the control plane comes in. It acts like the sophisticated air traffic controller and logistics manager, orchestrating everything from a higher, more strategic level.
The brains of the operation.
Kind of, yeah. Its main function is to constantly determine the best routing paths and configurations across the entire network. It uses sophisticated routing protocols such as OSPF, that's Open Shortest Path First, RIP, which is Routing Information Protocol, and BGP, Border Gateway Protocol.
Those are some acronyms.
They are. It uses these protocols to continuously exchange routing information among routers. These protocols are essentially the languages routers use to talk to each other, sharing updates on network conditions, available paths, potential congestion.
Okay.
This exchange allows the control plane to build and maintain comprehensive, up-to-the-minute maps of the entire network, identifying the most efficient, least congested, and often most secure routes for data to take.
What's fascinating here, especially for our business students listening, is how this separation allows networks to be incredibly robust for moving data,
Right.
while also being highly intelligent for finding those optimal paths.
Exactly. The control plane typically operates separately from the data plane, which is absolutely crucial for efficiency and scalability. It means the complex calculations for pathfinding don't slow down the actual forwarding of data packets.
That makes sense.
And it's both distributed, with intelligence spread across many routers collaborating, and yet it can be centrally managed or configured for flexibility and policy enforcement. This dual approach is fundamental to identifying those telecommunications and data communications technology fundamentals. It lets you appreciate how modern networks achieve both speed and reliability.
Okay, so if the network layer is our digital postal service and routers are the sorting offices, what does the actual letter or digital package look like? We call this a datagram, or more commonly an IP packet. When you send any kind of digital information, whether it's a simple text message, a massive image file, or streaming video, that data isn't sent as one giant, unwieldy chunk, right?
Yeah. No, definitely not. It's intelligently broken down into these smaller, more manageable IP packets. And once they reach their destination, these individual pieces are meticulously reassembled, much like putting together a puzzle, to reconstruct the original data.
So every packet needs instructions.
Exactly. And every one of these IP packets essentially has two main parts, a header and a payload. Think of the header as the sturdy envelope, complete with all the crucial details the Postal Service needs to deliver your letter accurately.
Okay, the addressing info.
Right, this overhead information is absolutely vital for the delivery process. It includes the source IP address, that's the unique identifier of the machine sending the data, and the destination IP address, pinpointing the intended recipient.
Source destination. Got it.
There's also a sequence number. This is a really vital piece of information. It ensures that when all those broken down packets arrive at their destination, they can be put back together in the correct order to restore the original data exactly as it was.
Prevents digital chaos, like you said, getting pages out of order.
Exactly. Imagine receiving pages of a report scrambled up. The sequence number prevents that. The header also contains other technical details like the type of service, various flags indicating how the packet should be handled, and other relevant data necessary for the transmission to occur smoothly.
Okay, that's the header, the envelope. Then we have the payload. This is the exciting part, right? The actual message itself.
That's it. This is the bulk of the packet, carrying the real data, your text, images, video, or whatever valuable information you're sending. And for sensitive business data like financial reports or proprietary designs, it's often heavily encrypted for security.
Super important.
Absolutely. This encryption ensures that only the intended recipient can read its contents, which is a critical aspect of formulating a risk assessment and developing an appropriate security strategy. These IP datagrams, these packets, they are absolutely essential components of the TCP/IP suite.
The foundation of the internet.
Pretty much the foundational set of protocols for the entire internet. They work hand in hand with other protocols like TCP, Transmission Control Protocol, which ensures reliable order delivery, and UDP, User Datagram Protocol, which prioritizes speed over guaranteed delivery. Together, they form the very core of how our devices communicate, making everything from email to video calls possible.
So let's connect this to the bigger picture for the business students listening. Why is understanding this packet structure so foundational?
Well, understanding the IP datagram structure is foundational for really configuring network connections, services, security, and management. It's about knowing precisely what's inside that digital box you're sending and receiving. For example, those source and destination IP addresses. They're critical for configuring routing paths and establishing firewall rules to control traffic flow. The sequence number directly impacts reliability and reassembly paramount for applications where data integrity is key, like financial transactions or medical records.
Makes sense.
Recognizing the payload and its potential for encryption highlights the non-negotiable need for robust cybersecurity strategies. This knowledge isn't just theoretical, it's a critical outcome that enables you to make informed managerial decisions about your company's network infrastructure, how it's protected, and how efficiently it operates. It's about being well-equipped to manage the underlying technology that powers all modern business communication.
Okay, here's where it gets really interesting. It's almost like learning the foundational language of the internet itself. Every single device connected to an IP network needs a unique address, a digital street sign, if you will, to be found and to communicate effectively. For decades, IPv4 was that address. But what is an IPv4 address at its most basic level? And how is it structured in a way that allows so many devices to find each other?
Excellent question. An IPv4 address is, simply put, a numeric identifier assigned to each machine or node on an IP network. It literally pinpoints its specific location, much like a physical street address. Without it, your laptop wouldn't know where to send that report. And Google servers wouldn't know where to send your search results back to. It's fundamental.
Okay, so what does it look like?
In terms of its format, an IPv4 address consists of 32 bits of information. Now, 32 bits sounds like a lot, maybe, but they're logically divided into 4 sections. Each of these sections contains 8 bits. We call these sections octets, or bytes.
4 octets, 8 bits each.
Exactly. And this segmentation is crucial because it allows for a structured, hierarchical approach to addressing, which helps routers make quick decisions about where to send things.
So we often see something like 172.1.12.125. That's the dotted decimal format we see, right? But the machine is really seeing binary.
Precisely. The common format we see, dotted decimal notation, like your 172.10.102.1125, that's purely for human readability. Makes it easier for us.
How much easier?
But for the machine, its actual representation is in binary notation. For instance, that same address is 101010101010101010101010. Each octet can range from 0 to 255 in decimal. Why? Because 8 bits allow for 2 to the power of 8, or 256, unique values starting from 0 up to 255.
Okay, 0 to 255.
This hierarchical addressing scheme is incredibly powerful. It allows for a theoretical maximum of about 4.3 billion unique addresses. That's 2 raised to the power of 32 possible combinations. The scalability was a key design choice for the early internet.
And there's some key terminology here, too.
Yes, to truly understand IPv4, it's important to grasp some key terms that define these parts. First, a bit, smallest unit of visual info, just a 1 or a 0. Then, an octet, or byte. That's simply a group of 8 bits. Then we have the network address, sometimes called the network ID. This is the portion of an IP address that uniquely identifies the network itself. Like in 172.8.12.125, maybe 172.20 is the network address. All machines on the same network share this exact network address. Finally, the node address, or host ID. This is the portion that uniquely identifies an individual machine on that specific network. So like 18.125 in our example. This part must be unique for every single device on that network. It's how your specific laptop is distinguished from your phone on the same Wi-Fi, for example. This brings us to a really critical historical point, How did we originally organize these billions of addresses? Early internet designers, anticipating different network sizes, created classes of networks based on their intended scale. This older approach, it was known as classful addressing.
Classful.
And it rigidly placed a fixed dividing line between the network part and the host part of an IP address. And this division, it was determined simply by looking at the first octet of the address.
So it was kind of like saying, okay, if your address starts with this number, you automatically belong to a really large neighborhood. And if it starts with that number, you're in a small one, like fixed sizes.
Precisely. Let's quickly review these classes. Not because they're used much now, but because understanding their limitations is key to seeing why we needed to evolve. It's important history.
Got it. Historical context.
Class A networks were designed for a small number of very, very large organizations. Think major government agencies or early tech giants. Their first octet ranges from 1 to 126. The default subnet mask, which we'll get to, was 255.0.0.0. This allowed for up to 126 networks, but each one could contain over 16 million hosts. Host speaker. Wow, 16 million. That's huge. Expert speaker. Huge. Imagine giving an entire state its own phone book, even if only a few towns were actually populated. That's the kind of potential waste we saw. 10.0.0.1 is a common example you might see in documentation for Class A private space. Host speaker. Okay, expert speaker. Class B networks were for medium-sized organizations. Their first octet ranges from 128 to 191 with the default subnet mask of 255.25.0.0. This provided for up to about 16,000 networks, each supporting over 65,000 hosts. Still pretty big. 172.1c.0.1 is an example often used in the Class B private range. Host speaker, okay, smaller than A, but still large. Expert speaker. Class C networks were the most numerous, intended for smaller organizations. The first octet ranges from 192 to 223, and the default subnet mask was 255.255.255.0. This meant up to 2 million networks, but each one was limited to only 254 usable hosts. 192.168.0.3.1 is a very familiar example, right? You often see that in home routers. Host speaker, yeah, definitely see that one. 254 hosts, that's much smaller. Expert speaker, much smaller. And beyond these three main classes, Class D addresses, starting 224, 239, were reserved for multicast purposes, sending data to multiple hosts simultaneously, useful for things like video conferencing streams. Host speaker, okay, expert speaker. And Class E addresses, starting 240, 255, were reserved purely for experimental purposes.
So what does this all mean for you as future business and IT leaders listening? Well, understanding these classful distinctions, even though they're largely historical now, is actually pretty crucial. It helps you grasp why early network designs face significant challenges. This rigid system often led to massive waste of IP addresses. Organizations were often forced to take a network class, like a Class B, that was far larger than they actually needed, leaving millions of addresses just unused.
A huge inefficiency.
Yeah. This historical context really illuminates why flexibility became the Internet's most critical design challenge. It perfectly sets the stage for more adaptive and efficient solutions like CIDR, which we'll definitely discuss next. It's an essential part of identifying those telecommunications and data communications technology fundamentals and seeing how they evolve to address real-world limitations. Okay, so beyond the standard A, B, C classes, there are some special IPv4 addresses with very specific, very practical roles. These are vital for network functionality and especially troubleshooting. One of the most important is the loopback address. It's 127.0.1. You might also see it represented as 127.x.x. What's this address actually used for?
Right, the loopback address. It's used to test the connectivity of a device with itself. Effectively, it's a way for a computer to talk to itself.
Talk to itself. How does that help?
Well, if you ping 127.0.0.1 from your command prompt and you get a reply, you know your device's internal TCP/IP software stack is working correctly. Even if it can't reach the outside world, you know the basic software plumbing is okay. It's a crucial first step in almost any network troubleshooting scenario. Is the problem on this machine or outside this machine?
Gotcha. Good first check. And then there are two addresses that define the very boundaries of a network segment, right? These aren't assigned to individual devices.
Exactly. The network address has all its host bits set to 0. For example, if your network is defined as 192.168.1.0 with a standard Class C mask, that .0 address signifies the entire network segment itself, not a specific device. It's like the street name without a house number.
Okay, identifies the whole street.
Right. Conversely, the broadcast address has all its host bits set to 1. So for that same 192.168.1.0 network, the broadcast address would be 192.168.1.255. This address is used to send data to all hosts on that particular network segment simultaneously. It's useful for certain network discovery protocols like DHCP discovering servers.
Send to everyone on the block.
Okay. But perhaps most practically significant, especially for most organizations and home users today, are private IP addresses. These are defined in a document called RFC 1918. These are special ranges of IP addresses that are not routable on the public internet.
Not routable, meaning?
Meaning they can only be used within private networks, like your home Wi-Fi or a corporate LAN. They aren't unique globally, only locally. For a device with a private IP address to communicate with the public internet, it needs to go through a router that performs network address translation, or NAT. We'll talk a lot more about NAT soon.
Okay, NAT is the bridge.
Exactly. The RFC 1918 private address ranges are, for Class A, 10.x.x.x, that's a massive range, 10.0 and 0.0 to 10.255.255.255.255, often used for very large private networks. For Class B, 172.168.x through 176.255.35x, a decent chunk. And for Class C, 192.168.x.x or 192.168.0.0 to 192.168.255.255. This is probably the most common one you see configured in home routers.
That 192.168 range, definitely familiar. This concept of private addresses is really central to how many modern networks function, isn't it?
Yeah.
From the smallest home network to the largest corporate LANs.
Absolutely central.
It directly impacts managerial issues in data communications because it allows organizations to use a vast number of internal addresses without needing to purchase expensive public ones for every single device.
Huge cost saving and address saving.
Right. And maybe more importantly, it led to that critical workaround, NAT, which prolonged IPv4's life, enabling many, many more devices to connect to the internet than the original 4.3 billion public IPv4 addresses would ever allow on their own. Understanding these special addresses is a key aspect of identifying network infrastructure and appreciating how we efficiently manage and expand our digital networks. Okay, so we have these IP addresses, which identify individual devices and their networks. But how do devices actually know if they're talking to a neighbor? Someone right there on the local network or someone, on the other side of the world? This is where the subnet mask comes in.
Yeah.
How does this clever bit of digital architecture act like a partition within your digital address book?
That's a great analogy, the partition. A subnet mask is another 32-bit number, just like an IP address, but its sole purpose is to help distinguish between the network part and the host part of an IP address.
Network versus host, okay.
It does this by having ones in the network part and zeros in the host part. So, for instance, a common subnet mask you see is 255.255.255.0 in dotted decimal notation.
Right, the Class C default.
Exactly. And that translates to 111.111.111.111.111.111.0000000 in binary. That long string of ones identifies the network portion. How does it make the decision? A local neighbor or remote server?
That's where a simple yet really powerful binary operation comes in. A device performs a logical AND operation on its own IP address and its configured subnet mask.
A logical AND.
Like in programming.
Exactly like that, bit by bit. The result of this AND operation is its network address. Now here's the clever part. Any other IP address on that same network will yield the exact same network address when AND with the same subnet mask.
So it compares the results.
Right. It performs the AND on the destination IP address too. If the resulting network IDs match its own, the destination is local. If they don't match, it knows the destination is remote. This seemingly simple operation allows devices to make those crucial routing decisions millions of times a second.
Fascinating. And what are the real-world benefits of this clever division for an organization? This concept of network segmentation, often called subnetting, sounds like it has some pretty big implications for how we design and manage networks.
Oh, it absolutely does. And it's vital for designing a logical network design for any given set of requirements. Think about these three core benefits for a business.
Okay.
Firstly, it leads to improved network performance. By dividing a large, potentially sprawling network into smaller, more focused subnets, traffic gets localized. Think of it like organizing a massive open-plan office into smaller departments.
Yeah, it keeps the noise down.
Exactly. Conversations or data traffic stay within the department, the subnet, unless they specifically need to go to another one. This significantly reduces overall network congestion and cuts down on unnecessary broadcast traffic, which can be a real drag on performance. A large, flat network with too many devices all shouting at once will experience severe performance degradation. Subnetting prevents that.
Makes sense. What else?
Secondly, it makes for easier management. Breaking networks into smaller, more manageable pieces simplifies administration and troubleshooting. It's a classic divide-and-conquer approach to network organization. Much easier to pinpoint and resolve issues within a smaller subnet than across a giant network.
Okay, performance management.security.
And thirdly, yes, critically, subnetting leads to enhanced security. Subnets can effectively isolate network domains by address space. A router sitting between subnets can act as a firewall, controlling exactly what traffic is allowed to pass between those segments.
Like checkpoints.
Precisely. This makes it much harder for issues like a denial of service, DOS attack, or malware to spread uncontrollably across an entire network. You can contain the damage. This capability is fundamental to formulating a risk assessment and developing an appropriate security strategy for any modern organization. It allows you to build a structured, resilient, and more secure network.
Okay, so the old classical system we talked about earlier, with its fixed Class A, B, and C networks.
Sure.
It was like trying to build a city where every single block had to be exactly the same size. super rigid.
Yeah, very inflexible.
And it quickly became a major bottleneck, right? Often leading to wasted IP addresses if an organization needed a network size that didn't perfectly fit one of those predefined classful boundaries. This inflexibility became a serious problem as the internet just exploded with new devices and networks.
That's exactly right. And that's where classless interdomain routing, or CIDR usually pronounced CIDR, became such a game changer. It gave us the flexibility we desperately needed.
Okay, CIDR.
Classless routing is a more modern, much more efficient approach that allows the dividing line between the network part and the host part of an IP address to fall anywhere along that 32-bit string.
Anywhere, not just on the octet boundary.
Anywhere. It's completely unrelated to those historical Class A, B, or C boundaries. That's precisely why it's called classless. It basically discards those old restrictive rules.
So no more rigid boundaries.
Yeah.
But how does the network know where the lines are drawn then, if it's not based on the first octet?
Ah, good question. In classless routing, the subnet mask becomes the explicit tool that tells devices exactly where the network, subnet, and host portions lie. It's no longer implicitly defined by the IP's initial digits.
The mask is king now.
Exactly. The mask acts like a special lens through which to view the IP address, precisely defining the boundaries wherever they need to be. The real magic here is in borrowing bits. Subnetting in the CIDR world involves borrowing bits from the host portion of an IP address to create a new subnet portion in the middle.
Borrowing bits from the host part. How does that work?
Well, think of it this way. The more bits you borrow from the host part to use for subnets, the more subnets you can create within your overall network. But the trade-off is you'll have fewer host bits left, meaning fewer hosts available within each individual subnet. Conversely, if you borrow fewer bits for subnets, you'll have fewer subnets, but more host bits remaining, allowing for more hosts per subnet. It's a direct trade-off you design based on your needs.
Okay, a balance between number of networks and size of networks. And CIDR notation makes this super clear, right? That slash notation.
Absolutely. CIDR notation is really elegant and efficient. It's represented by a forward slash followed by the number of bits used for the combined network ID and subnet ID. So if you see an IP address like 192.168.89.12724, that 24 explicitly tells you that the first 24 bits are dedicated to identifying the network and subnet. The remaining 8 bits, 32 total minus 24, are for the host on that specific subnet. This notation is far more efficient and descriptive than relying on those old classful masks.
Much more precise.
Exactly. And the ability to calculate subnets and hosts based on borrowed bits is a core skill for any network professional. It's a direct outcome of mastering this topic for business students interested in an IT career. This precision and flexibility are what allows for effective logical network design, maximizing the use of IP addresses, and creating network structures that precisely match organizational needs rather than being constrained by rigid classes. This is fundamental for the design, integration, and selection and implementation of communication solutions we discussed earlier. It enables you to identify and select appropriate networking components for the job.
Okay, this is the invisible handshake, happening billions of times a second across the internet, determining where every single packet should go next. How does your device know if it's sending a packet to your local printer, maybe just a few feet away, or to a web server thousands of miles away? It all comes back to the IP address and that crucial subnet mask. Can you walk us through this decision-making process?
Yeah, it's surprisingly elegant in its simplicity, really. Let's consider end systems or hosts like your computer or your smartphone. When your device wants to send a packet, it first looks at the destination IP address written on that packet.
Okay, where's it going?
Right. Then it compares this destination IP address with its own network ID. And how does it know its own network ID? It derives it by performing that logical AND operation between its own configured IP address and its configured subnet mask.
Okay, does the AND on itself gets its network ID?
Exactly. Then it does the AND on the destination IP. This comparison yields two possible paths. Local communication. If the destination IP address's calculated network ID matches its own network ID, the host knows the destination is on the local subnet, essentially, a neighbor.
Doesn't need the router.
Exactly. In this scenario, it doesn't need a router. Instead, it will send out an ARP request, that's Address Resolution Protocol, to find the destination device's physical MAC address on the local network segment. Once it has the MA address, it can directly forward the packet to that device using Layer 2 switching, remote communication. However, if the destination IP address's calculated network ID does not match its own network ID, the host determines that the destination is on a remote network.
somewhere else.
Somewhere else. It knows it can't reach this destination directly. So what does it do? It sends the packet to its default gateway.
The router.
Right. The default gateway is simply the IP address of the router on its local network, the literal gateway to the rest of the world, or at least other networks.
And then the routers take over from there, making their own decisions using the same logic.
Exactly right. Routers, in turn, play that pivotal role. They receive those packets that are intended for remote destinations. Upon receiving a packet, a router will again use the relevant subnet mask, often from its own interface configuration or routing table, to compare the packet's destination IP with the entries it has stored in its routing table.
A router's map.
Its map, exactly. The routing table is like a detailed map listing all the networks the router knows about, and crucially, the next hop, which is usually the IP address of the next router in the path, and the outgoing interface, the physical port, to use to forward the packet onwards towards its ultimate destination. This continuous process, looking at the destination IP, applying the subnet mask, consulting the routing table, forwarding, is how data traverses the internet, ensuring packets find their way across potentially dozens of diverse networks.
And this really highlights the architecture needed for troubleshooting, too.
Absolutely. This entire process highlights the core architecture of networks and is fundamental to facilitating effective troubleshooting techniques. If a device can't communicate, checking its IP address, its subnet mask, and its default gateway configuration is often the first, most logical step in diagnosing the problem.
Why those three?
Well, think about it. An incorrect subnet mask could lead a device to mistakenly believe a remote host is actually local, causing it to never send traffic to the default gateway where it needs to go. Or an incorrect default gateway address means it simply can't reach any remote networks at all. These fundamental checks allow you to apply appropriate network troubleshooting techniques for a given scenario. It's a critical skill outcome for maintaining network resilience and efficiency.
Okay, so with the internet growing exponentially, especially in the 90s and early 2000s, IPv4 addresses were quickly running out. Remember that theoretical limit of 4.3 billion addresses? It started to look like a looming crisis.
Yeah, real cliff edge.
So what was the ingenious workaround that kept the internet running on IPv4 for so much longer than expected, preventing a complete collapse? What is network address translation, or NAT, and why was it such a game changer?
NAT truly saved the day for IPv4. The main idea behind NAT is surprisingly simple in concept, yet incredibly effective in practice. NAT translates private IP addresses, those RFC 1918 addresses like 192.168.1.x, used extensively within your local network.
The internal ones.
Right, the internal ones. It translates them into global or public IP addresses before those packets are forwarded out to external networks, typically the vast expanse of the internet.
So like a disguise.
Kind of. Imagine an entire apartment building sharing just one public phone number for all outbound calls. Everyone inside has their own extension, but to the outside world, all calls seem to come from that single number. That's NAT at work, multiplexing connections.
Okay, that makes sense. So it really served two critical purposes, didn't it?
Yeah, absolutely. NAT served two key drivers that were absolutely essential for the internet's continued growth. Firstly, and this was its primary role initially, was to conserve internet global address space. It allows countless devices on a private network, each with its own unique private IP address, to share just a single public IP address when communicating out to the internet. This means a single public IP address, maybe assigned by your ISP, can represent hundreds or even thousands of internal devices. Massive conservation, host speaker, huge saving, expert speaker. And secondly, NAT significantly increases network security. By hiding the internal IP addresses and the overall structure of a private network from external networks, NAT adds a layer of obscurity. It's almost like a digital disguise, as you said. It makes it much harder for outside entities to directly target or even discover internal devices, because all they see from the outside is the router's public IP address, not the individual private IPs sitting behind it.
Okay, conservation and security. And how does it operate in practice? Where does this happen?
In operation, NAT typically runs on a router or sometimes a dedicated firewall device. This device acts as the gateway, sitting precisely between the private, we call this the inside network, and the public outside network.
A border guard.
Exactly. It translates addresses on the fly, it seamlessly intercepts outbound traffic, rewrites the source IP address from private to public before sending it on its way, keeps track of that translation, and then reverses the process for any incoming replies destined for that internal device.
That's clever.
It is. And this concept of NAT is a prime example of design integration and the selection and implementation of communication solutions under significant constraint. It really demonstrates how network engineers adapted existing technologies to address a critical scarcity issue running out of addresses while simultaneously bolstering network security.
Like killing two birds with one stone.
Pretty much. From a managerial perspective, it highlights how a clever technical solution can defer costly infrastructure upgrades, like buying huge blocks of public IPs, and buy valuable time for a more long-term solution, like the transition to IPv6. It's a key aspect of understanding managerial issues in data communications, illustrating that constant balance between technical feasibility, cost, security, and operational continuity when selecting appropriate hardware and software.
Okay, so just like there's more than one way to, I don't know, brew the perfect cup of coffee, there must be different ways to implement NAT, each with its own use case depending on the specific needs of a network.
Certainly. There are three primary flavors of NAT you'll typically encounter in network design and management.
Three main types.
Okay. First, there's static NAT. This creates a one-to-one persistent mapping between a specific inside local IP address, your private IP, and an inside global IP address, a public IP. Think of it like a dedicated, unlisted direct phone line assigned just to one person.
One private equals one public. Always the same.
Always the same mapping. For example, if you have an internal web server on 192.168.1/10, you might statically map it to a specific public IP, like 203.0.113.5. This is ideal for internal servers that need to be consistently accessible from the internet, like a company's public web server, an email server, or maybe a VPN endpoint.
Things people need to reach from outside.
Exactly. The drawback, of course, is that it requires one unique public IP address for each such internal host you want to expose publicly, so it doesn't conserve addresses nearly as much as other types.
Okay, that's static. What's next?
Next is dynamic NAT. This is a bit more flexible and conserves addresses better than static. Dynamic NAT maps unregistered inside local IP addresses to a pool of available inside global IP addresses on a first-come, first-served basis.
A pool of public IPs.
Right. So a pool of public IPs is pre-configured on the NAT device. As internal devices initiate connections to the outside, they dynamically check out or grab an available public IP from this pool for the duration of their session. Once the connection ends, or maybe a timer expires, the public IP is returned to the pool for someone else to use.
So you only need enough public IPs for simultaneous users.
Precisely. It requires a pool of public IP addresses, but it's more efficient than static NAT because you don't need one public IP for every internal device, only for the maximum number of devices that need to access the internet concurrently.
Okay, static, dynamic.
Yeah.
But the third sounds like the most common one.
And the third, yes, is overloading, which is more commonly known as port address translation, or PAT. This is by far the most common and widely used form of NAT. And it's the real hero that stretched IPv4's life well beyond its expected limits.
NAT. Okay, how does it work?
PAT allows multiple inside local IP addresses to map to a single inside global IP address.
Multiple to one. How?
By using different port numbers for each outgoing connection. This is a many-to-one translation. Think back to our apartment building analogy. With PAT, hundreds of people in that building can use the same single public phone number, but each person uses a different extension number, a source port number, when making an outbound call.
Ah, the port number keeps track.
Exactly. The NAT router maintains a detailed translation table. It tracks the private IP and source port, the public IP, which is the same for everyone, and the unique translated source port it assigned for that specific connection. So when a reply comes back to that one public IP address and a specific port number, the router checks its table and knows exactly which internal device, private IP, and original port to send it back to.
That's really ingenious.
It is. The impact of PAT cannot be overstated. It's the primary reason why IPv4 addresses haven't completely run out yet. It allows potentially thousands of internal users and devices to connect to the internet using just one single public IP address. This is fundamental to how most home and small office networks operate today. It effectively enabled IPv4 to serve billions more devices than it was ever designed for.
Wow.
Yeah. And PAT is a brilliant, if complex, example of how a relatively simple protocol can be extended to address massive scalability issues within telecommunications and data communications. It really shows how configuring network connections, services, security, and management for given requirements often involves these kinds of creative solutions that push the boundaries of the initial design. For business students, understanding these different NAT flavors, static, dynamic, and PAT, is crucial for selecting and implementing communication solutions, especially when you're balancing cost, public IPs aren't free, security needs, and the requirement for external accessibility for specific company services. It's a testament to the adaptive nature of network engineering and how we leverage existing hardware and software to meet constantly evolving demands.
Okay, so to fully grasp NAT and, talk about it effectively, especially with technical teams, you really need to understand its specialized language. These terms help us define precisely where an IP address sits in relation to the NAT device. Is it on the inside network or the outside? Is it the local address or the global one the world sees? Can you quickly clarify these key terms for us?
Of course, these four terms are absolutely fundamental to speaking the language of NAT. First, the inside local address. This is the actual IP address configured on an internal host within your private network. For instance, if your laptop has 10.1.1.0 assigned by DHCP, that's its inside local address. This is typically a private IP address, RFC 1918, and is only meaningful inside your private network.
Okay, the real private IP on my machine.
Exactly. Second, the inside global address. This is the public IP address that an inside local host gets translated to, making it identifiable to the outside world. So when your laptop at 10.1.1.CIR talks to the internet, the NAT router might change its source IP address to, say, 55.1.1.1, your ISP-assigned public IP. That 55.1.1.1 is the inside global address. It's the address the outside world sees when your internal device initiates communication outwards.
The public face of my internal device.
Got it. Right. Third, the outside global address. This is simply the public IP address of an external host, like a web server out there on the internet, as seen by the entire outside world. If you're connecting to a server at 99.1.1.2, that's its outside global address. This address is globally routable and unique on the public internet.
The public IP of the thing I'm talking to.
Correct. And fourth, the outside local address. This one's a bit less common, but important conceptually. This is the IP address that an external host is known by within your private network. Often, this is exactly the same as the outside global address, 99.1.1.2 in our example. But it can be translated by the NAT device if needed for specific internal compatibility reasons. Maybe you have an internal system that needs to think it's talking to a private IP. This is less common in standard NAT setups, but can occur in more complex scenarios.
Okay, so inside local, outside global, outside local. These terms allow network professionals to precisely describe the source and destination addresses as they actually traverse the NAT device, understanding exactly how they're being transformed at each step.
Precisely. And for business students, mastering this terminology isn't just about technical precision. It's really about understanding the security implications and the traffic flows across your entire enterprise. When you're developing a professional network proposal to address a business problem, clear communication with technical teams is absolutely paramount.
Yeah, you need to speak the same language.
Exactly. Using these terms correctly demonstrates a solid grasp of how data is routed and secured, how NAT contributes to your overall security strategy by hiding internal IPs, and how it impacts network manageability. This knowledge is fundamental to ensuring your proposals are technically sound and effectively address the underlying managerial issues in data communications.
Okay, despite the incredible ingenuity of subnetting, CIDR, and especially NAT, all these brilliant patches and workarounds that extended IPv4's life well beyond its original design, the fundamental issue remained, right? IPv4 address exhaustion. It was still a ticking clock.
A very loud ticking clock by the late 2000s.
Yeah. The explosion of mobile devices, IoT, Internet of Things, gadgets, smart everything, and billions of other connected devices just made it crystal clear that we needed a truly new, vastly more expansive foundation for the Internet's addressing scheme. We couldn't just keep patching IPv4 forever. So what exactly is IPv6 and why is it so critical for the Internet's future?
IP version 6, or IPv6, is designed specifically to solve that core problem. It provides an almost unlimited number of addresses. We're talking about a scale that's hard to even comprehend, honestly. It ensures the Internet's continued growth and scalability, supporting not just current devices, but literally billions, even trillions of future connections. It's truly the next chapter for the internet, essential for what we sometimes call the Internet of Everything.
And a big shift is moving away from NAT.
Yes, one of the most significant shifts with IPv6 is its move away from that private-public network model that NAT necessitated for IPv4. While NAT was a brilliant solution for IPv4 scarcity, it did introduce complexity and could sometimes interfere with true end-to-end reachability for certain applications, making peer-to-peer difficult, for example.
Right.
IPv6 prioritizes global IP addresses for virtually all devices. The ideal is that every IPv6-enabled device has its own unique, publicly routable IP address. This simplifies network design significantly and enhances application functionality by allowing true end-to-end communication without intermediaries constantly rewriting addresses on the fly.
So less complexity, more direct connections.
Ideally, yes.
Yeah.
Now, IPv6 does have concepts similar to private addresses, primarily the self-assigned link local ones used for communication just on the local network segment. But the default approach, the architectural preference, is global reachability.
This sounds like a massive undertaking, though, shifting the entire internet from one system to another.
Oh, it is. It's a huge ongoing transition. And this shift from IPv4 to IPv6 isn't just a technical upgrade. It's really a strategic imperative for any organization or nation looking to stay competitive and innovative in the digital age.
Strategic imperative. Why?
Because understanding the drivers and benefits reflects that knowledge outcome of exploring the current and future impact and direction of these technologies. In a world moving rapidly towards ubiquitous connectivity, where everything from industrial sensors and smart cities to countless personal devices will rely on having unique, addressable identities, IPv6 is the absolute bedrock for that future. It directly addresses the managerial issues in data communications by providing the necessary address capacity and, hopefully, a simplified network architecture for future growth without the complex constraints and workarounds that NAT imposed on IPv4.
Okay, when you hear 128 bits for an IPv6 address, it sounds huge, and it really is. Like if IPv4's 4.3 billion addresses were barely enough for everyone on Earth to maybe have half an address each.
Yeah, not even close now.
IPv6 could give a virtually unique address to every single grain of sand on every beach in the world, and then probably do it again hundreds of times over. It's truly mind-boggling. But IPv6 brings far more to the table than just sheer quantity, doesn't it? What are the key features that make it so much more powerful than just more addresses?
Absolutely. More addresses was the driving need, but IPv6 is a complete redesign, offering profound benefits for scalability, efficiency, and security. The most obvious, yes, is the vast address space. IPv6 addresses are 128 bits long, a massive leap from IPv4's 32 bits. This provides that astounding 3.4 by 138 addresses. That's 340 undecillion. To put that into perspective, it's a quadrupling of the bit size, but it expands the address space by 2 to the power of 96 compared to IPv4.
Mind-blown.
Yeah. This immense address space inherently supports massive scalability, accommodating billions, even trillions of new devices without needing complex translation like NAT or other workarounds. This directly supports our knowledge outcome about the future impact and direction of telecommunications technologies.
Okay, huge scale. What else?
IPv6 offers incredible flexibility. It includes features like route summation, which allows for more efficient routing by summarizing large blocks of addresses into smaller routing table entries, making routers faster. Devices can easily have IP addresses in multiple networks simultaneously, simplifying things like connecting to multiple ISPs, multi-homing.
Easier connections.
Yeah, and there are plug-and-play features and self-assigned addresses through something called SLAC, Stateless Address Auto-Configuration. This makes device configuration much easier, and often totally automatic devices can basically figure out their own address without needing a DHCP server in many cases.
Nice.
Plus, renumbering a network changing your address block, which was a huge headache in IPv4, imagine having to reassign every single IP in a large corporation is significantly facilitated in IPv6. It makes it easier to switch service providers or change network topologies without extensive manual reconfigurations.
Okay, scale, flexibility. What about speed and security?
Good points. IPv6 also boasts a simpler header design compared to IPv4. It's streamlined with fewer fields and fixed lengths to make processing by routers easier and faster. This allows for more efficient forwarding of trillions of packets even as network speeds continue to increase. And critically, built-in security is a core tenet. IPsec, Internet Protocol Security, which provides encryption and authentication, is not just an optional add-on in IPv6 like it often was in IPv4. It's baked right into the protocol. It's a mandatory part of the spec, providing native encryption and authentication for network traffic. This directly contributes to formulating a risk assessment and developing an appropriate security strategy, protecting data at a fundamental level across the entire network.
Built-in security is huge. And how does it work alongside IPv4? They have to coexist, right?
Absolutely. Since IPv4 isn't disappearing overnight, IPv6 environments almost always employ coexistence strategies. These include dual stacking, where devices and networks run both IPv4 and IPv6 protocols simultaneously. This is very common. Tunneling, which encapsulates IPv6 packets inside IPv4 packets to allow them to traverse IPv4-only networks. Tunneling, or translation techniques like NAT64, which allow IPv6-only devices to communicate with IPv4-only resources, like older websites. Tunneling. This speaks directly to the idea of alternatives available in hardware, software, and transmission facilities for current and future communication solutions. We need these bridges during the transition.
That makes sense.
And for business students, understanding these benefits is really crucial for selecting appropriate wired, wireless, and optical fiber networking components in the future, and to explore how these technologies impact current and future network direction. IPv6 isn't just about an address upgrade. It's about enabling innovation and growth across virtually every sector, from smart manufacturing to global e-commerce. It impacts how you'll design future networks, implement security, and manage the ever-increasing number of connected devices, fulfilling multiple knowledge outcomes crucial for your career growth.
Okay, I gotta say, 128 bits of hexadecimal digits. It still sounds like an absolute nightmare to remember and work with, right? An IPv6 address like 2001.0 db8.000.000.000.9c5 a.000cc. Yeah, that definitely isn't rolling off the tongue.
No, it's a mouthful. Looks daunting at first glance, for sure.
You said there are elegant rules, right? A kind of digital shorthand to make IPv6 addresses much more manageable for us humans.
That's right, thankfully. The IPv6 address format itself, as you noted, uses hexadecimal digits, 0, 9, and AF. These 128 bits are divided into 8 16-bit blocks, sometimes called quartets, or more accurately, hextets, since they contain hex digits.
8 blocks separated by colons.
Exactly. 8 16-bit blocks separated by colons, and since each hexadecimal digit represents 4 bits, each 16-bit block has 4 hex digits. So you've got 8 groups of 4 hex characters separated by colons. That's your full 128 bits.
Okay, 8 groups of 4 hex digits, and what's this digital shorthand that makes them less terrifying?
There are 2 main truncation rules that vastly improve readability and make them much shorter in many cases. The first rule is simple: dropping leading zeros. Within each 16-bit block, any leading zeros can just be omitted, so 0db8 becomes db8, 0b80 becomes b80, and 083 becomes d3. If a block is all zeros, like 0000, it simply becomes 0. You can't remove trailing zeros, only leading ones.
Okay, drop the leading zeros in each block. That helps.
It does, but the second rule is even more powerful. It's the double colon rule. A single contiguous block of one or more all-zero blocks, like 00000000, can be replaced by a single double colon.
A double colon replaces multiple 0 blocks.
Yes, but only one sequence of 0 blocks. It acts like a spring, compressing a series of zeros down to just for example, that long address you read, 2001.0db 8000000000.9c5a.00cc. Then we can use the double colon for the 0.0 sequence, 2001.db8.db8.d3.9c5acc, much shorter.
Wow, yeah, much better. 2001.db8.db8.d3.9c5acc.
Yep.
Wait, why only once, though?
Ah, good catch. The double colon can only be used once per address. Why? To avoid ambiguity. If you used it twice, say 2001.abcd.1, you wouldn't know how many 0 blocks each represented. Did the first one represent 2 blocks and the second one represent 3, or vice versa? You wouldn't know how to reconstruct the full 128-bit address, so only one local allowed per address.
Got it. 1 double colon max.
It's a clever way to keep the address size down for human readability while maintaining that critical machine-level precision. And mastering this shorthand is a practical skill. It helps immensely in configuring network connections and for reading network documentation, logs, command output efficiently.
Yeah, I can see that.
For professionals, quickly parsing IPv6 addresses and logs or configuration files is crucial for diagnostics and management. It directly contributes to the skill of configuring network connections and services for a given set of requirements. It's a small detail, maybe, but a powerful one in daily operations that simplifies these otherwise unwieldy addresses.
Okay, so IPv6 is not just about having trillions upon trillions of addresses. It fundamentally rethinks how devices communicate. You even mentioned it does away with the traditional broadcast method entirely. Why no broadcast traffic in IPv6, and what new address types replace it or handle those functions?
That's a really key difference from IPv4. In IPv6, you won't find broadcast traffic as we knew it. Why? Because broadcasts can be very inefficient. They send traffic to all devices on a network segment, whether those devices need the information or not. It's like shouting in a crowded room, mostly noise.
Okay, so broadcasts are inefficient. What does IPv6 use instead?
Instead, IPv6 primarily uses multicast traffic for reaching multiple devices. Multicast is much more efficient and targeted. Devices specifically join a multicast group if they're interested in receiving that traffic. It's more like subscribing to a newsletter than getting junk mail.
Opt-in versus shouting at everyone. Makes sense. So if broadcast is out, what are the primary address types we really need to understand in IPv6?
Right, let's break down the main categories. First, we still have unicast addresses.
Okay.
These are for one-to-one communication, just like in IPv4, but IPv6 gives us more specific categories within unicast. Global unicast addresses, GUAs. These are your standard publicly routable addresses. They're directly analogous to public IPv4 addresses and are designed for end-to-end reachability across the global internet. They typically fall within the 2000.3 range, meaning they start with a 2 or 3. These are the main way devices communicate over the public internet. Host speaker. Okay, GUAs are the public ones. Expert speaker. All right. Then we have link local addresses. These are fascinating and super useful. They're not routable outside the local link or network segment. They're primarily used for communication within a single network segment, like discovering neighbors or routers. They always start with FE 80.10. Your computer probably has one right now. They're handy for temporarily LAN, this initial device configuration, and they're fundamental for that stateless address auto-configuration, SLAC process we mentioned, allowing devices to get an IP address automatically without needing a DHCP server. Host speaker, link local. Only works on my local network wire or Wi-Fi.
Yeah.
Expert speaker, exactly. Then there are unique local addresses, ULAs. These are intended for internal, non-routing purposes within a larger site or organization, but they are designed to be nearly globally unique. This makes it very unlikely that two different organizations will accidentally use the same ULA range, preventing conflicts if networks ever merge. They replace the older problematic site local addresses and fall within the FC00.7 range. They serve a similar function to IPv4 private addresses, RSC 1918, for internal network communication across multiple subnets within an organization, but without relying on NAT host speaker. ULAs are like private addresses, but smarter, expert speaker. Kind of, yeah. And of course, there's a loopback address, 0.1, just one colon. This is the direct equivalent of 127.0.11 in IPv4 and is used for testing a device's own network stack. Ping 0.1 is the IPv6 equivalent of ping 127.0.0.1.
Okay, GUAs, link local, ULA, loopback. That covers unicast. What about reaching multiple devices?
That's where multicast addresses come in. These enable one-to-many communication. Packets sent to a multicast address are delivered efficiently by the network only to all the interfaces that have specifically registered as members of that multicast group. You can easily spot an IPv6 multicast address because they always start with FF. Specifically, they fall in the FS00.8 range. This is how IPv6 handles many functions that IPv4 previously used inefficient broadcast for, like router discovery or finding DHCP servers, but in a much more targeted and efficient way. Host speaker. Multicast. Replaces broadcast mostly. Okay. Expert speaker. And finally, we have anycast addresses. This is a truly innovative concept in IPv6, though it existed minimally in IPv4. An anycast address identifies multiple interfaces, often geographically distributed servers providing the same service. But here's the magic. A packet sent to an anycast address is delivered by the routing system only to the closest one, closest usually meaning in terms of routing protocol distance or hops.
Only the nearest one gets it.
Exactly. This is incredibly powerful for providing resilient and geographically distributed services, like critical DNS root servers or content delivery networks, CDNs. Users are automatically routed to the nearest available server, which improves performance and provides automatic failover if one server goes down.
Yeah, anycast sounds really useful for big services.
It is. And understanding these different address types, unicast, GUA, link local, ULA, multicast, anycast, is absolutely key for effective IPv6 network design and for selecting appropriate networking components for a given set of requirements. For instance, knowing how link local addresses enable stateless address auto-configuration, SLAC, helps you understand understand a powerful feature for self-configuring devices, directly addressing a core knowledge outcome about how IPv6 can streamline network management. This level of detail helps students identify those crucial telecommunications and data communications technology fundamentals, particularly in the context of advanced addressing schemes and how they enable modern network capabilities.
Okay, now, for our business students listening, this is really where the rubber meets the road, isn't it? Designing an IPv6 network isn't just some technical exercise for the engineers down the hall. It's a profound strategic decision. It impacts everything from network performance and security to long-term operational costs and, crucially, future scalability. From a managerial standpoint, why is a well-thought-out IP address plan so absolutely critical in the IPv6 world?
You've hit it exactly right. From a managerial standpoint, an effective IP address plan is absolutely critical. It goes way beyond just uniquely addressing every device. It's fundamental for facilitating ongoing network management across the board. We're talking about everything from monitoring network health in real time to enabling faster fault detection and resolution, ensuring efficient resource provisioning as you add new services or users, guaranteeing performance management for critical applications, and of course, underpinning robust security policies.
So it touches everything.
Everything. This is a core part of managerial issues and data communications, and truly a cornerstone of designing a logical network design that works now and scales for the future.
Okay, so how does a good IPv6 address plan actually impact something tangible, like, say, routing performance or how you implement security policies? Can you give some examples?
Yeah, definitely. It has a massive direct impact. Let's look at a few examples. Routing performance. This is huge in large networks. A hierarchical IPv6 allocation strategy significantly enhances performance. Imagine your organization gets a large block, maybe a 48, from its internet service provider. You might then strategically allocate smaller blocks down the chain, maybe 52 blocks to your core routers, then 56 blocks for different geographic regions or large departments, then 60 blocks for individual sites or buildings, and finally the standard 64 for each individual subnet or VLAN.
Wow, nested blocks.
Exactly. This structured hierarchical approach drastically improves routing efficiency. Why? Because routers can summarize routes. Instead of needing a separate routing table entry for every single 64 subnet, a router higher up might only need one entry for the entire 56 region, or even the 48 for the whole organization. This massively reduces the size of routing tables and minimizes the volume of routing protocol updates flying around the network. For large enterprise networks, this is crucial for keeping traffic moving fast and efficiently.
Smaller routing tables, faster routing. Makes sense. What about policies?
A well-structured address plan also dramatically simplifies router policies. For example, imagine you allocate separate IPv6 blocks specifically for voice over IP, VoIP traffic versus standard data traffic. Now, it becomes much easier to configure quality of service QoS policies on your routers. You can create a simple rule that says all traffic originating from the VoIP address block gets high priority. This ensures clear calls even during periods of heavy network usage without complex packet inspection.
Nice. And security.
And for security functions, a thoughtful IP address plan is an absolute game changer. IP address-based security policies like access control lists, ACLs, implemented on routers and firewalls, become much simpler to define, manage, and audit. If all your servers are in a specific 60 block, you can write very clear rules controlling access to that block. A coherent plan allows administrators to quickly quarantine an entire compromised network segment just by blocking its prefix, or easily redirect specific traffic flows, like all traffic from the guest Wi-Fi block, through an intrusion detection system for analysis. This directly supports the skill outcome of formulating a risk assessment and developing an appropriate security strategy.
Those are really compelling reasons. So what are the overarching goals of putting together such a strategic plan? What's the actual business case for investing time and effort in this?
The goals of an IPv6 address plan are essentially its business case. First and foremost, provide address capacity. This is fundamental, ensuring you have enough IPv6 addresses allocated for all current and foreseeable future infrastructure and end-user devices. This allows for seamless growth without hitting allocation walls. Second, enable and control communications. Defining precisely which devices should be able to communicate with each other internally and with the internet based on specific business needs and your defined security posture. Third, enable communications via supported applications, ensuring that critical business applications like video conferencing, large data transfers, or real-time control systems receive the appropriate network treatment, like QoS, based on their communication requirements, often tied directly to their specific IP address ranges. And finally, a really elegant goal: facilitate visual mapping. A brilliantly designed plan allows administrators and even managers to visually identify a device's potential location, application type, or organizational unit simply by looking at its IPv6 address.
Like reading the address tells you something.
Exactly. For example, an address like 2001.db8.1a.8c29.64 could be structured so that the 1a signifies the southern region, 8c signifies the marketing department, and 29 signifies Site 2, maybe even with a bit indicating its voice traffic. This kind of embedded information directly relates to the skill outcome of designing a logical network design that is intuitive, manageable, and aids troubleshooting.
That's incredibly powerful for management and operations. Are there specific strategies or techniques for actually allocating these vast blocks of IPv6 addresses? It seems daunting.
Yes, there are several IPv6 allocation techniques architects use, each offering different advantages depending on the goals, growth, security, simplicity. Monotonic allocation. This is the simplest. You just assign sequential address blocks as needed, like subnet 0, subnet 1, subnet 2. Easy to track, but might not leave room for future expansion in the middle. Sparse allocation. This intentionally spreads out the initial allocations, leaving large unallocated blocks between the allocated ones. This provides flexibility for future contiguous growth, helping with renumbering or expanding networks later without needing to add lots of new routes. Best fit allocation. This allocates the smallest available block that meets a specific immediate demand. Less critical maybe with IPv6's vast space compared to IPv4, but still useful for managing specific constraints or resources. Random allocation. This deliberately randomizes address assignments within a larger block. From a security perspective, this makes it harder for attackers to footprint or guess the network's allocation plan and identify potential targets. Prefix delegation. This is more of an automated mechanism, often using DHCP v6. It allows a router or server, like an ISP's, to automatically allocate entire blocks of IPv6 addresses, like a 56 or 60, to downstream requesting routers, like your home or office router. This makes setup much easier for customers.
Okay, different strategies for different needs. Any general guidelines?
Some general block allocation guidelines include: use your baseline IPv4 plan as a data point, maybe for estimating the number of subnets needed, but don't just copy it rigidly. Define all your IPv6 address spaces, early public GUAs, internal ULAs, any coexistence technologies you'll use. Document your network architecture, especially the routing layers. Enumerate all your IP address space policies, routing, QoS, filtering, ACLs, because these will influence your allocation. Prioritize universal criteria like geography higher up in the allocation layers, and more specific criteria like application type lower down. And a practical tip: try to plan on nibble boundaries. A nibble is 4 bits or 1 hex character whenever possible. This makes the addresses much easier to read, allocate visually, and manage.
Wow, that's comprehensive.
It needs to be. This comprehensive approach to IPv6 address planning is a cornerstone skill. It ensures that you, as future professionals, can design and implement robust communication solutions, configure efficient network management, and apply appropriate security strategies. It fulfills multiple learning and skill outcomes crucial for your career growth. It's really about leveraging the incredible potential of IPv6 to build resilient, scalable, and secure networks that truly meet business needs, rather than just patching the limitations of the past. This level of strategic thinking is what sets successful network architects and IT managers apart.
Okay, imagine this scenario. You're the network admin for a university with thousands of students bringing laptops, phones, tablets, or maybe a large corporation with hundreds of employees, each with multiple devices. Imagine trying to manually assign an IP address, a subnet mask, a default gateway, and DNS server addresses to every single one of those devices.
Oh, wow. Yeah, that would be an absolute nightmare.
Right. The sheer scale would be overwhelming. The potential for errors, like typos leading to duplicate IP address conflicts, and just the wasted time would be enormous. This is where DHCP, the Dynamic Host Configuration Protocol, comes in. It's truly the unsung hero of network automation, streamlining network management, and making our lives infinitely easier. How does it work? It's a magic.
You're absolutely right. DHCP is indispensable in almost any network larger than a handful of devices. The primary role of DHCP is to act as a network service that automatically and dynamically leases IP addresses and other vital network configuration settings like the subnet mask, default gateway, DNS servers, even things like domain name or time server info to client devices when they connect to the network.
Leases them, like renting an address.
Exactly like renting an address for a specific period, the lease duration.
Yeah.
This DHCP service usually resides on a dedicated server or, very commonly in smaller networks, integrated into a router. When your laptop connects to the Wi-Fi, for instance, one of the first things it does is shout out looking for a DHCP server to get its network credentials.
And that process has a name, right?
DORI.
That's the one. This lease generation process follows a simple yet elegant four-step sequence, often remembered by the acronym DORI. Discover. The client device, newly connected, broadcasts a DHCP discover message, essentially shouting, "Is there a DHCP server out there? I need an IP address and configuration." Offer. An available DHCP server, or multiple might respond, hears this discovery message and replies with a DHCP offer, proposing an available IP address and other configuration settings from its pool. Request. The client typically accepts the first offer it receives and sends back a DHCP request message, formally asking to use that specific offered IP address. Acknowledge. Finally, the DHCP server that made the offer acknowledges the client's request with a DHCP ask message. It marks the IP address as leased in its database so it doesn't offer it to anyone else, and tells the client, okay, that address is yours for this lease period. This whole DORI process typically takes just a fraction of a second, making seamless connectivity a reality for users. That's incredibly efficient. So what are the most significant business and managerial benefits of using DHCP? Why is it so important?
The importance of DHCP for business and network management really cannot be overstated. First, it minimizes configuration mistakes. Manual IT assignment is incredibly prone to human error typos, duplicates, wrong masks. DHCP eliminates almost all of that. Host speaker, fewer mistakes, fewer help desk calls. Expert speaker, exactly. Second, it provides automatic configuration of endpoints. This eliminates the need for technicians or users to manually set up IP settings, saving massive administrative effort, especially in large dynamic environments with many transient devices like guest Wi-Fi or BYOD policies. Host speaker saves a ton of time. Expert speaker, huge time saver. Third, it makes it easy to implement changes. If your network configuration needs to change, say you deploy a new internal DNS server, you simply update that setting once on the central DHCP server. As clients renew their leases, they automatically pick up the new configuration. No need to touch every single device manually. Host speaker, centralized control, nice. Expert speaker. Fourth, it recycles IP addresses efficiently. When devices disconnect or their lease expires, their IP addresses are automatically returned to the pool and can be reused by new devices. This is crucial for environments like coffee shops, airports, or even large offices where devices come and go frequently. It prevents you from running out of addresses in your assigned range. Host speaker. Good for transient environments. Expert speaker. And finally, importantly, the DHCP server typically logs leases. It keeps a record of which IP address was assigned to which device, using its MC address, and when. These logs are invaluable for troubleshooting connectivity issues and for security auditing purposes.
Okay, so DHCP is clearly ideal for most user devices, laptops, phones, etc. But there must be situations where static, unchanging IPs are still needed, right? You wouldn't want your main server changing its address randomly.
Absolutely. While DHCP is fantastic for client devices, it's important to differentiate DHCP from static IP configuration. You need to use static IP addresses manually configured and permanent for devices that require a fixed, unchanging network identity. Think critical infrastructure, servers, web servers, file servers, domain controllers, routers, switches, firewalls, network printers, and often the DHCP server itself. These devices need a consistent, predictable address that never changes so other devices and services can reliably find them.
So servers get static, clients get dynamic via DHCP.
That's the general rule. Dynamic IP addresses assigned via DHCP are ideal for those end-user client devices like desktops, laptops, tablets, smartphones, and most IoT devices. These devices frequently connect and disconnect, or their exact IP address doesn't need to be permanent for them to function correctly. Key DHCP components you'll work with include the DHCP server itself, the DHCP client software on devices, the IP address pool, called a scope, the subnet mask, the default gateway address, DNS server addresses provided, the lease duration setting, and the scope itself, which defines that pool of available IP addresses and all the associated options.
This sounds crucial for network management.
It is. Efficient network management is a core outcome for our students, and DHCP is a prime example of software that enables it. It directly contributes to the skill of configuring network connections and services for a given set of requirements with minimal overhead and maximum reliability. Correctly configuring DHCP scopes, ensuring they're large enough, have appropriate lease times, don't overlap with other scopes causing conflicts, and provide the right gateway and DNS info is absolutely critical. This knowledge is paramount for identifying telecommunications and data communications technology fundamentals.
Okay, think about this. You type google.com into your browser, hit enter, and bam, instantly you're there. You don't type in some obscure number like 142.250.191.111.
No, thankfully not.
Right. But how does your computer know where google.com actually lives in the vast digital landscape? The answer, as many know, is DNS, the domain name system. Can you explain how this internet's phone book actually works? It seems like magic sometimes.
It does seem like magic, but it's really just clever engineering. DNS is truly fundamental to how we navigate the internet. The basic purpose of DNS is to translate those human-readable domain names that we find easy to remember, like nytimes.com or tarleton.edu, into the machine-readable IP addresses, IPv4 or IPv6, that computers actually use to locate each other on the network.
Okay, name-to-number translation.
Exactly. This translation is absolutely necessary because web browsers, email clients, and pretty much all other network applications interact using IP addresses to establish connections, not domain names. We humans are great with names, computers are great with numbers. DNS is the essential bridge that connects those two worlds.
So it's like a global distributed lookup system. Who are the main players involved in the typical DNS lookup? It can't just be one giant server, right?
No, definitely not. That would be impossible to manage and incredibly slow. The process of a DNS lookup involves a hierarchy of specialized DNS servers, each with a specific role, working together like a well-coordinated team. First, there's the DNS recursor, sometimes called a recursive resolver. Think of this as the diligent librarian who does the legwork for you. It's usually a server run by your ISP or maybe a public service like Google's 8.8.8.8. It's designed to receive DNS queries from your client machine, your computer. It's responsible for making all the necessary additional requests out to other DNS servers to track down the correct IP address on your behalf.
Okay, the recursor does the searching for me. Where does it start?
It starts at the top with the root name servers. These are like the library's master index or the very top directory. They are the first step in resolving any domain name globally. They don't know the IP address for google.com themselves, but they do know where to find the servers responsible for the .com domain. They point the recursor to the appropriate TLD name server. There are 13 logical root servers globally, distributed and replicated for resilience, forming the absolute top of the DNS hierarchy. Host speaker, root points to TLD. Okay, expert speaker. Next is the TLD name server. Top level domain. This is like a specific book rack for a category like .com, .org, .net, .edu, .gov, etc. It hosts information for these top level domains. When asked about google.com, the .com TLD server doesn't know the final IP, but it does know the addresses of the authoritative name servers specifically responsible for the google.com domain. It points the recursor to those. Host speaker. TLD points to the final authority. Expert speaker. Exactly. Finally, we reach the authoritative name server. This is the dictionary itself, the ultimate source of truth for a specific domain. This server actually holds and is officially responsible for maintaining the DNS resource records for that specific domain name, e.g. google.com. It provides the definitive IP address or addresses back to the recursor.
Wow, okay. Recursor asks root. Root points to TLD. TLD points to authoritative. Authoritative gives the answer. That sounds like a lot of steps. Can you simplify how a typical DNS lookup flows, maybe in a scenario where the answer isn't already cached anywhere?
Sure, let's simplify the main flow of an uncached DNS lookup. 1. You type google.com into your browser. Your computer sends a query to its configured DNS recursive resolver, e.g. your ISP server, asking what's the IP for google.com. 2. The resolver, assuming it doesn't have the answer cached, starts at the top. It queries a DNS root name server. Where can I find info about .com? The root server responds with the address of a .com TLD name server. 3. The resolver then queries that .com TLD name server. Where can I find info about google.com? The TLD server responds with the addresses of google.com's authoritative name servers. 4. Finally, the resolver sends its query to one of google.com's authoritative name servers. What's the IP address for google.com? The authoritative name server checks its records and returns the definitive IP address. Find G, 142.250.191.10. 4. Finally, the resolver sends its query to one of google.com's authoritative name servers. 5. The DNS resolver receives this IP address and sends it back to your web browser. 4. Finally, the resolver sends its query to one of google.com's authoritative name servers. 6. Now your browser has the IP address it needs and can initiate a direct connection, like an HTTP request, to Google's server. This whole lookup process usually happens incredibly fast, often in just milliseconds, thanks to caching.
Oh, okay. DNS caching must be absolutely essential to speed this up even more and reduce the load on those higher-level servers.
Exactly. Without caching, DNS would grind to a halt. To speed this all up, DNS caching plays a huge role. DNS information, like the IP address for google.com, is temporarily stored or cached at various levels, right inside your web browser itself for a short period. At your operating system level, sometimes called a STUM resolver, And very importantly, within the recursive DNS resolver at your ISP or public DNS provider, they cache answers for popular domains for a time determined by the record's TTL. This caching drastically reduces the number of queries that need to go all the way up the hierarchy, making subsequent lookups for the same domain almost instantaneous.
And all this information is stored in specific record type.
Yes, all of this DNS information is stored in DNS resource records. These are specific entries within the DNS database that define how domain names map to IP addresses and other critical services. Key types you'll encounter include records for mapping a name to an IPv4 address, AAA records Quad A for mapping a name to an IPv6 address, CNAE records for creating aliases, canonical names, pointing one name to another, MX records, mail exchanger, to specify which servers handle email for a domain, PTR records, pointer, used for reverse DNS lookups, finding a name from an IP address, NS records, name server, to delegate authority for a subdomain to other name servers, SOA record, start of authority, containing administrative info about the zone. And each record also has that important TTL, time to live value, specified in seconds. This tells resolvers how long they are allowed to cache that specific record before they should ask for it again, controlling how quickly changes to DNS records propagate across the internet.
Understanding this whole DNS hierarchy, the lookup process, caching, and these record types seems absolutely critical.
It is. It's critical for configuring network connections and services correctly for any organization. If DNS isn't working, nothing that relies on names works. It's also foundational for developing a professional network proposal, because reliable DNS is essential for user accessibility to business applications and websites. If users can't resolve your company's domain name, they simply can't reach your services. This directly relates to several knowledge outcomes and skill outcomes by enabling you to effectively manage and troubleshoot connectivity issues related to name resolution, a core component of identifying telecommunications and data communications technology fundamentals.
Okay, so if DNS is the internet's phone book, translating names we trust like mybank.com into numbers, what happens if someone malicious slips a fake number into that phone book? Or somehow intercepts your request and gives you the wrong number, redirecting you to a fake website that looks real?
That's a huge concern and a very real threat. It directly impacts trust and security online in a fundamental way.
This is where DNS-SEC, DNS security extensions comes in, right? How does it add that crucial layer of cryptographic authentication to protect against malicious tampering and ensure the integrity, the trustworthiness of the internet's phone book?
That's exactly its purpose. The problem DNS-SEC addresses is that standard DNS, as originally designed, is inherently vulnerable to various attacks. You mentioned the key ones, DNS spoofing or DNS cache poisoning, where attackers inject false DNS records into a DNS server's cache, causing it to give incorrect IP addresses to users, man-in-the-middle attacks, where attackers intercept DNS queries and responses between you and the DNS server, altering them on the fly, man-in-the-middle attacks. All of these can lead to users being unknowingly redirected to fake, malicious websites that might steal credentials, phishing, or distribute malware. This poses significant security risks.
So DNS-SEC is essentially like putting a digital signature or a tamper-proof seal on those DNS records.
Precisely. That's a great way to think about it. The solution is DNS-SEC. It uses cryptographic authentication, specifically public key cryptography, to verify two critical things. One, that the DNS records received actually came from the legitimate, authoritative name server for that domain. Two, and crucially, that the records have not been altered or tampered with while in transit. This ensures that when your computer resolves a domain name like mybank.com to an IP address using a DNS-SEC validating resolver, you can have high confidence that you're being directed to the actual legitimate website, not a fraudulent imposter.
Okay, authenticity and integrity. How does DNS-SEC actually work its magic to create this trust? It sounds complex.
It is fairly complex under the hood, but the core concept relies on a system of public and private key pairs and digital signatures to create a robust chain of trust that spans the entire DNS hierarchy, from the root down to individual domains. First, within a DNS zone, like example.com, there are zone signing keys. ZSK. A private ZSK is used to cryptographically sign the actual DNS resource records, like the A record or MX record within that zone. These signatures are stored in special SAVROSIG records, resource record signatures. The corresponding public ZSK is then published in a DSK record within the zone, so resolvers can use it to verify the signatures.
Okay, ZSK signs the records.
Then to protect the ZSK itself, there are key signing keys, KSK. This is another public-private key pair used specifically to sign and authenticate the public ZSK. The public KSK is also published in a DSKey record.
KSK signs the ZSK. Okay, layers of signing.
Exactly. And this forms a chain of trust. The entire process involves cryptographic signing at each level of the DNS hierarchy. The root zone is signed, the TLD zones, like .com, are signed, and finally, individual domains, like example.com, are signed by their operators. Delegation signer, DS records, are used in the parent zone, example.com zone, to point to and authenticate the public KSK of the child zone, EOG example.com. This creates an unbroken cryptographic chain linking all the way back to the trusted root zone servers.
So Resolver can check the signatures all the way up.
Yes, a DNS SEC validating resolver can follow this chain of DS and DNS key records and RSIG signatures all the way back to a trusted root key. If everything verifies cryptographically at each step, it knows the final answer, the IP address, is authentic and hasn't been tampered with. There are other related DNS SEC records too, like NSEC or NSEC3 records, which are used to securely prove that a requested domain name doesn't exist, authenticated denial of existence, preventing certain types of attacks.
Wow. This raises a really important question for businesses, doesn't it? How do you protect your digital presence, your brand reputation, from these sophisticated cyber attacks that target the very foundation of Internet navigation?
DNS SEC is a crucial part of the answer. While it's not universally deployed yet, its adoption is growing. For our students, formulating a risk assessment and developing an appropriate security strategy to mitigate these kinds of DNS-based risks is a key skill outcome. Without DNS SEC validation, the Internet's phone book remains vulnerable to manipulation, which could lead to devastating phishing attacks, malware distribution, and significant reputational damage for businesses whose names are spoofed. It's fundamentally about ensuring the authenticity and integrity of our most basic online navigations, making it harder for attackers to hijack user traffic and protecting the trust anchors of the Internet. This understanding is paramount for building a more secure digital future and is a vital component of selecting appropriate and secure communication solutions.
Okay, so we've talked about IP addresses getting data to the right computer on the network. That's layer 3, the network layer, doing its job. Huge step. But what happens next? What if that computer is running multiple different network applications simultaneously? Maybe it's acting as a web server, an email server, and maybe even a game server, all running on the same machine with the same IP address.
Yeah, that's a very common scenario for servers and even for client machines running multiple apps.
Right. So how does the incoming data know which specific application it's actually intended for? If the IP address just gets it to the machine, how does it find the right program? This is where ports and sockets come into play, right? Acting like the specific digital front doors or maybe extension numbers on that computer for different applications.
That's precisely it. A port, or more formally a port number, is a numerical label assigned to a specific process, that is, a running program or service on a host computer that is designed to receive or send network data. Think of it exactly like a specific door or an extension number for a particular application running on that server or computer.
So it's not a physical thing, but a logical label.
Exactly. It's not a physical door, but a logical identifier, a 16-bit number that uniquely identifies a specific service or application endpoint within that host. For example, as we mentioned, a web server application like Apache or Nginx is typically configured by default to listen for incoming web page requests arriving at port 80 for unencrypted HTTP, or port 443 for encrypted HTTPS. An email server might listen on port 25 SMTP for sending mail, and maybe port 110 POP3 or port 143 IM-half or their secure versions 995, 993 for clients retrieving mail.
Okay, so the port number tells you the specific application or service on that machine. But what then is a socket? I hear that term used a lot too.
Good question. Building on the port concept, a socket is the unique combination of an IP address and a port number. It defined a very precise, unique endpoint for network communication.
IP address plus port number socket.
Exactly. So if your web server has the IP address 10.43.3.87, and it's also, for some reason, running an old telnet service on port 23, the specific socket address for that telnet service on that particular host would be written as 10.43.3.87.23. This unique pairing ensures that incoming data packets know exactly which application on which host they are intended for. The network stack uses this combination to deliver the data to the correct running process.
And a session is between two sockets.
Right. A session, particularly for connection-oriented protocols like TCP, represents the continuous, managed exchange of information between two specific sockets, one on the client machine and one on the server machine, or potentially even two sockets on the same machine.
Okay. And these port numbers, they have a defined range and different categories, right? It's not just random numbers.
No, definitely not random. Port numbers range from 0 all the way up to 65535, which is 216.1. And they're generally categorized into 3 types, managed by INA, the Internet Assigned Numbers Authority, to maintain order. Well-known ports, ranging from 0 to 1023. These are strictly reserved for universally recognized, widely used standard services and protocols. Everyone agrees that port 80 is for HTTP, port 443 for HTTPS, port 20 and 21 for FTP, File Transfer Protocol, port 22 for SSH, Secure Shell, port 23 for Telnet, though hopefully not used much anymore, and port 53 for DNS. Operating systems often require special privileges to run services on these low-numbered ports.
Okay, 01023 are the famous ones.
Then we have the registered ports ranging from 124 to 49151. These are assigned by INA to specific applications or services upon request from software vendors or organizations. Many common applications use ports in this range. Think database servers like MySQL on 3306, remote desktop protocols, and many others. They're registered to avoid conflicts, but not as universally standard as the well-known ports.
Registered, so kind of reserved, but less famous.
And finally, the dynamic and/or private ports, ranging from 49152 to 65535. These are typically not assigned to specific server applications. Instead, they are used dynamically by client applications for their outbound connections. When your web browser connects to a web server on port 443, your computer dynamically assigns a random port from this high range for its end of the connection, the source port. These are temporary, ephemeral ports used just for the duration of that specific communication session and then released.
Ah, the client picks a high number for its side. Okay. And beyond the most common ones like HTTP, DNS, SSH, there are many other essential protocols with well-known or registered ports that network pros encounter all the time, right?
Oh, absolutely. Things like TFTP, Trivial File Transfer Protocol, often port 69, NTP, Network Time Protocol, on port 123, which is crucial for time synchronization, LDAP, Lightweight Directory Access Protocol, port 389 or 636, for accessing directory services like Active Directory, SMB, Server Message Block, port 445, used heavily by Windows for file and printer sharing, and syslog, port 514, for sending system log messages across the network. Knowing these common ports is vital.
Why is understanding ports so fundamental?
Well, understanding ports is absolutely fundamental for configuring network connections, services, security, and management for practically any given set of requirements. Think about firewalls. Firewall rules almost always revolve around allowing or denying traffic based on destination and sometimes source port number.
Open port 80 for the web server.
Exactly. If your web server needs to be publicly accessible, you must create a firewall rule that allows incoming traffic on port 80 and/or port 443. If you want to allow secure remote administration via SSH, you need to open port 22. If you want to block insecure telnet, you explicitly deny traffic to port 23. This control at the port level is a critical aspect of identifying telecommunications and data communications technology fundamentals, and it directly contributes to developing an appropriate security strategy by allowing you to control access precisely at the application layer, not just at the IP address level. It's about selecting and configuring appropriate software components and security settings for a given set of requirements.
Okay, inevitably, things go wrong. When your network isn't behaving as expected, maybe you suddenly can't access a website, your network printer just won't show up, or a critical internal server becomes unreachable, it's time to put on your network detective hat.
Yep, grab your trench coat and magnifying glass,
Yeah.
digitally speaking.
Exactly. These command line tools are your essential magnifying glass and fingerprint kit for diagnosing these tricky addressing and connectivity problems. They help you systematically uncover the root cause of these digital mysteries. So which tools are absolutely indispensable for our budding network detectives out there?
Right. These tools are your first line of defense, your basic toolkit. Let's look at some of the indispensable ones you'll use constantly. The ping command is probably your very first and most fundamental tool. It's simple but powerful. It uses ICMP, Internet Control Message Protocol, messages, specifically echo request and echo reply, to test basic IP connectivity to another host. You can ping by IP address or by FQDN, fully qualified domain name like www.google.com.
Ping just sees if you can reach it at all.
Basically, yes. It tells you if packets can get there and back and roughly how long it takes, latency. If you can successfully ping an IP address but you can't ping its domain name, that immediately tells you the problem is likely related to DNS resolution, not basic network connectivity itself. Super useful diagnostic clue.
Isolates the problem domain.
Exactly. And ping has useful options like ping Janine T on Windows, or just ping without options on Linux, for a continuous ping to monitor ongoing connectivity or watch for intermittent drops. Ping DN count lets you send a specific number of requests. And for testing IPv6 connectivity, you typically use ping 6 or sometimes ping day 6.
Okay, ping is number one. What's next for checking my own configuration?
That would be ipconfig on Windows systems, or its older cousin ipconfig on Linux macOS, though it is generally preferred now on modern Linux. These are vital for displaying the detailed TCP/IP configuration for all your network interfaces or connections. This shows you your assigned IP address, your subnet mask, your default gateway address, and the addresses of the DNS servers your machine is configured to use.
All the vitals in one place.
Precisely. And ipconfig has some key troubleshooting options. Ipconfig release, followed by ipconfig renew, are essential for diagnosing DHCP issues. This forces your device to give up its current IP lease and request a brand new one from the DHCP server. Also, ipconfig displays shows you the contents of your local DNS cache, and ipconfig flush DNS clears that cache out. This is your go-to command if you suspect you have stale or incorrect DNS information cached locally, causing resolution problems.
I've lost the DNS cache, yeah. Heard that one helps sometimes.
It often does. For Linux users, as I mentioned, the ip command is the more modern and versatile utility. Commands like ipicado show to see addresses or iproute show to see the routing table are often preferred over ipconfig for viewing and managing TCP/IP settings, offering more granular control and information. The hostname command is simple but useful. It just displays the configured name of the current host computer. Good for confirming you're on the right machine.
Okay, ping ipconfig ip hostname. What about specifically testing DNS?
For that, the nslookup utility is key. It's available on both Windows and Linux macOS. It's specifically designed for troubleshooting DNS resolution problems. You can use it to directly query specific DNS servers to resolve domain names into IP addresses, forward lookup, or IP addresses back into domain names. Reverse lookup using PTR records. It supports both a quick non-interactive mode, e.g. nslookup www.google.com, and a more detailed interactive mode where you can set options and query different record types. Host speaker, nslookup for DNS checks. Expert speaker. And finally, especially favored by network pros on Linux and macOS, is the dig command, which stands for Domain Information Grouper. Dig provides even more detailed and granular DNS information than nslookup. It gives you the query, the answer section, the authority section, timing info, really everything about the DNS response. It's often preferred for advanced DNS diagnostics.
Dig, okay. Sounds powerful.
It is, and applying appropriate network troubleshooting techniques for any given scenario is an absolutely essential skill outcome for anyone working in IT or networking. These command line tools are your foundational toolkit, your first line of defense in maintaining network resilience and efficiency. Knowing not just what these tools do, but when and how to use them effectively, and how to interpret their output, directly contributes to your professional growth and your ability to configure efficient network management. They enable you to systematically diagnose and resolve the inevitable connectivity problems that arise in any complex data communications environment, effectively helping you identify the architecture of networks to facilitate these troubleshooting techniques.
Okay, so knowing the tools is one thing, absolutely essential. But knowing what to look for and how to actually fix it, that's what makes you truly invaluable as that network detective. Let's talk about some of the common headaches, the real-world scenarios you're likely to encounter, and how you might approach diagnosing and resolving them.
Yeah, these are the everyday challenges you'll definitely face. First up, something that seems simple but can cause weird problems. Incorrect time problem. If a computer or network device has the wrong system time, even by a few minutes, it can disrupt critical services. This is especially true for authentication services, like Kerberos, used in Windows Active Directory, or validating TLSSL certificates, which often rely on precise time synchronization for security reasons. If clocks are too far off, authentication can just fail. Host speaker. Wow. Time affects logins. Expert speaker. Absolutely. Remedy. You'll need to verify that NTP, Network Time Protocol, which typically uses UDP port 123, is functioning correctly, and that devices are configured to synchronize their clocks with a reliable time source, like an internal NTP server or public ones. On Windows, the W32tmeter command line tool can help diagnose and manage NTP settings. And just as a side note, for applications needing extreme precision, like in financial trading or industrial control systems, there's also PTP, Precision Time Protocol, which offers down to nanosecond accuracy.
Okay, check the time. What's next? DHCP issues seem like they'd be incredibly common, especially in dynamic networks with lots of devices coming and going. What kinds of problems crop up there?
Oh, DHCP can definitely be a source of frustration. Common DHCP issues include Exhausted DHCP scope is a big one. If the range of available IP addresses defined in the DHCP scope is too small for the number of devices connecting, or if the lease times are set way too long, already weeks instead of hours or days in a busy guest network, the pool of available IP addresses can simply run out. New clients trying to connect won't be able to get an address and will fail to join the network, often getting a self-assigned AP address, 169.254.x.x. Host speaker ran out of addresses, need a bigger pool or shorter leases. Expert speaker. Exactly. Another issue is duplicate DHCP servers. If you accidentally have two active DHCP servers on the same network segment, maybe someone plugged in a rogue wireless router with DHCP enabled, ERIS, it can lead to chaos. Clients might get inconsistent configurations or conflicting IP address offers, leading to intermittent connectivity problems and duplicate ITs. Host speaker. Rogue DHCP servers, bad news. Expert speaker, very bad. Also misconfigured options. The DHCP server itself might be working, but configured incorrectly. It might be distributing the wrong default gateway address or incorrect DNS server settings. Clients will successfully get an IP address and mask, but they won't be able to reach anything beyond their local network, wrong gateway, or resolve domain names, wrong DNS. Host speaker, got an IP but can't go anywhere. Check the DHCP options. Expert speaker. Right. And finally, overlapping address pools. If you have multiple DHCP servers, which is fine for redundancy if configured correctly with different scopes, but their defined IP address pools accidentally overlap, they could both end up issuing the same IP address to different clients. This causes nasty IP address conflicts and communication failures for the affected devices.
Okay, lots to check with DHCP. Beyond DHCP, what about just basic network connection configuration issues on individual devices, like typos during manual setup?
Yes, these are often the simplest problems, but can be surprisingly common, especially if static IPs are used without good documentation. An incorrect IP address, or very commonly, an incorrect subnet mask. If either of these is wrong, the device won't be able to communicate correctly with other devices on the local network or reach its default gateway. If the subnet mask is wrong, the device might think a remote host is local and try to ARP for it instead of sending to the gateway, or think a local host is remote and unnecessarily send traffic to the gateway. Both fail. Host speaker. Mask has to be right for local remote decisions. Expert speaker. Crucial. A duplicate IP address is another serious issue. If two devices on the same network are accidentally assigned or configure the same IP address, it causes instability and communication failures for both devices as the network switches get confused about where to send traffic for that IP. Expert speaker. An incorrect gateway address configured on a device means it simply cannot send traffic to remote networks. Essentially, it's trapped on its local network segment and can't reach the internet or other internal subnets. The gateway address is a good first test here. And finally, incorrect DNS server addresses configured on the client, or a DNS server malfunction misconfiguration itself. This means your device can't resolve domain names into IP addresses. You'll see errors like server not found in your browser, even if you can ping public IP addresses directly, proving your basic IP connectivity and gateway are working. This points strongly towards a DNS issue.
Okay, so if you suspect DNS is the culprit, you can ping IPs, but not names. What's a quick best practice to diagnose whether it's your local DNS server or something bigger?
A crucial quick DNS troubleshooting best practice is this. Temporarily configure your device, or just use a tool like nslookup or dig to query well-known, reliable public DNS servers. Good examples are Google DNS 8.8.8.8 and 8.8.4.4, or Cloudflare DNS 1.1.1.1 and 1.0.0.1.
Bypass your usual DNS server.
Exactly. Try resolving the problematic domain name using one of these public servers. If you can successfully resolve the name using the public server but not using your locally configured DNS server, for example, your ISP's or your company's internal server, then you know the issue almost certainly lies with your local DNS server or its configuration, not with broader internet connectivity or the domain itself.
Narrows it down fast.
Very quickly. These common issues, time sync, DHCP problems, basic IP mask gateway DNS config errors, are the real-world challenges faced by IT support staff and network professionals every single day. Understanding them, knowing the tools to diagnose them, and knowing the steps to resolve them empowers you to configure network connections, services, security, and management effectively for any given set of requirements. And critically, it enables you to apply those vital troubleshooting techniques effectively when things inevitably break. This is exactly where your classroom knowledge translates directly into career-ready skills, preparing you for those industry-standard network certification exams. The ability to quickly identify and resolve a DHCP conflict, a DNS misconfiguration, or a simple gateway typo is invaluable in keeping any business operating smoothly and securely. Hashtag outro.
Wow, okay, what a deep dive today. We've really covered some ground. We journeyed from the fundamental structure of those digital packets, the datagrams,
The digital envelopes.
to the intricate dance of IPv4 addressing, its limitations, and the clever workarounds like NAT, then on to the vast future with IPv6 addresses.
The next generation.
All the way through the crucial back-office services of DHCP and DNS that make it all work automatically, and even got our hands dirty, digitally speaking, with essential command line troubleshooting techniques. We've truly seen the incredible, often invisible infrastructure that makes our interconnected world possible.
Indeed. And hopefully we've shown how network addressing is far more than just assigning numbers. It's fundamentally about designing a logical, efficient, secure, and scalable network. That's the foundation that underpins all modern telecommunications and data applications. For you, our listeners, particularly those heading into business and technology fields, understanding these concepts isn't just academic.
No, it's really practical.
It's foundational to navigating and hopefully shaping the digital world. It prepares you for those industry-standard network certification exams, yes, but more importantly, for a bright future in business and technology, where understanding the network is increasingly vital.
That's absolutely right. Remember what we said at the start. From the cloud to your coffee maker, everything is connected, and it all starts with data communications. Now you have a much better idea of the incredible infrastructure that makes that connection possible. From the tiny bits inside an IP datagram to the global addressing schemes like IPv6 that will route your data across continents in the future. Hopefully, this gives you a real shortcut to being well-informed. So if you've gained new insights today, or maybe had one of those aha moments where something finally clicked,
Hopefully few.
please take a second to like, subscribe, and definitely share this deep dive with your friends, your classmates, your colleagues. You really don't want to miss out on insider tips and insights that could help position you for a bright future in your chosen careers.
Yeah, help spread the knowledge.
And remember, for even more valuable resources links, further reading, maybe practice exercises, things that will supercharge your learning and help you on your journey, always check the description below. It's packed with information curated just for you.
It is. So as you go about your day, maybe interacting with dozens of network devices without even thinking about it, here's a final thought. Given the constant, relentless evolution of technology, the explosion of connected devices, and the persistent challenge of securing our digital infrastructure, how will the next generation of addressing schemes or network management protocols continue to balance those competing demands of efficiency, scalability, and security in an increasingly complex and interconnected world? What role will you play in shaping that future?
Great question to ponder.
Remember, strong connections aren't just technical, they're strategic. Until next time, keep your packets clean and your networks resilient.